Mr. Taru, in this math lesson, we're going to do a handful of examples where we're going to deepen our understanding of the relationship between the sum and roots of a polynomial and the coefficients that we see throughout that polynomial. We're just going to be taking a look at, well, Francois Viette's formula. We've already done a video. I'll put a link in the description for this relationship for quadratic equations. We have a few formulas for cubic functions, but for a quadratic, the sum of your roots is equal to negative b over a, and the product of these roots is equal to c over a, and these coefficients are what we recognize when we look at the general form of a quadratic. Ax squared plus bx plus c is equal to 0, where a is the coefficient of the squared term, b is the coefficient of the single degree term, and c is our constant. Well, if we look at a different scenario where we are specifically looking at a cubic function, then we're going to list off those coefficients as a, b, c, and d. And we see here that for the sum of the roots, the relationship is basically the same. You're going to do the opposite of the second coefficient over the leading coefficient, just like it is here with our general quadratic being ax squared plus bx plus c. The sum of the roots is equal to the opposite of basically the second coefficient in your polynomial, as long as those exponents are counting down by 1, over our leading coefficient. Now this formula here that we don't appear to have with a quadratic is the product of x sub 1 times x sub 2. Again, these subscripts, these are x sub 1, x sub 2, x sub 3 are the roots of our polynomial. If we multiply x sub 1 times x sub 2 plus x sub 1 times x sub 3 times, plus x sub 2 times x sub 3, well then that sort of combination of product and sum is equal to c over a. And with our cubic function, c is our third coefficient divided by our leading coefficient of a. And then if we go down to just looking at the product of our roots, then we have the opposite of d over a. Okay, now for a cubic function, d is our constant and a is our leading coefficient, just like it is with our product of roots for our quadratic equations, where it's c is our constant over a. So it's kind of the same pattern, constant over the leading coefficient, constant over the leading coefficient, but with a cubic function we have a negative here, and with a quadratic equation we have a positive ratio. So what's going on there? Well, we can see it as we look at our general form. For a general polynomial, f of x is equal to a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power. So as you look at this and I read this out, a subscript a sub anything is just the coefficients of each of our terms, and that same power, n minus 1, the power matching the subscript, that's going to be the power that's applied to the variables that are in our polynomial. Of course, we know a polynomial is a function who has one independent variable and all of the exponents are positive integers, going all the way down to, I'm including this just for teaching, where we see the powers of n going down and continuing to count down until you get to a power of 0. So all your polynomials effectively could come down to a constant as our last term. Not that that's necessarily guaranteed, because you could have some situation where your constant coefficient, if you will, is equal to 0. So your last term maybe is an x to the first or something like that. With real or complex coefficients, and a sub n is not equal to 0, so that just means that we're going to give you some formula here for a nth term polynomial. So a sub n, your leading coefficient, can't be equal to 0, because then you're kind of looking like at an n minus 1 degree polynomial. So these little formulas are just to make this sync with our general form of our polynomial, with roots of x sub 1, x sub 2, x sub 3, and so on and so on. You have the same number of roots in a polynomial as you have the degree. So the sum of our roots is going to be equal to, and I guess I could do it dot 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 up to x sub n here, is equal to the opposite of a sub n minus 1 over a sub n. That can be seen here with our specific formulas for quadratics and cubics, that we have the same ratio, the opposite of b over a, the opposite of b over a. But using the variables of a, b, c, and d and such, those coefficients, is only appropriate when we know exactly what degree our polynomial is. So we just have basically the second coefficient in our polynomial being divided by the leading coefficient of our polynomial in the opposite of that ratio. So these subscripts are just basically where you are along the list of coefficients in your polynomial, where your degrees start at some, highest power and then count down by 1. Then if you do x sub 1 times x sub 2 plus x sub 1 times x sub 3, then because we've gone we're going to continue that process of multiplying our roots, starting with x sub 1 to 2, 3, 4, 5, all the way down to x sub n. And then plus, so you're going to exhaust all the possibilities of having your first root times by every other successive root that your polynomial gives you until you get to that nth root. And then you just pick up with now x sub 2 and start that going with x sub 2 times x sub 3. So you count up in those subscripts, x sub 2 times x sub 4, all the way till you get to x sub 2 times x sub n, and then plus x sub 3, x sub 4, x sub 5 each time, starting at the next highest subscript and going till n, until you get that last product, which is x sub n minus 1 times x sub n. So this sort of combination of products and sum is going to be equal to, well, a sub n minus 2 over a sub n. And this doesn't necessarily seem like a general form, and the reason why is because I'm giving you a specific list of a product of 2 of our roots. And so that's why we have this a sub n minus 2. If we had a product of 3 of our roots, so if it was x sub 1 times x sub 2 times x sub 3, and then maybe x sub 1 times x sub 2 times x sub 4, and you kind of exhaust all those combinations of a product of 3 roots, then that's going to be a sub n minus 3 over a sub n. You'll see this in our final general formula down here in blue, and something's happening with our signs. We're going from positive to negative. Let's try that again, from negative to positive. So if we were looking at the sum of 3, the sum of the multiplication of 3 of the roots, you'd have a negative here in front of our fraction until we get down to nothing but just a straight product of all of our roots. That's going to be negative 1 to the nth power over a sub 0 times a sub n. So a straight sum of our roots is the opposite of the second coefficient divided by the leading coefficient, and a straight product of all of our roots is going to be negative 1 to the nth power, that's the degree of your polynomial, times the constant divided by the leading coefficient. And then there's just like this combination of what's going on in the middle. So what is that? Well, we have this sigma notation, which is showing up nothing more than the addition of all of these terms. And we got a big fancy subscript here, or notation below our sigma notation, where it says 1 is less than or equal to I sub 1, which is less than I sub 2, which is less than I sub 3, and I sub 4, basically talking about how many roots are you multiplying in each of these terms, all the way up to a sub n, which we see here in our last line. That is equal to, so basically this is our general form of each of these individual formula that relate this sum or combination of product and sums, or just straight products of our roots, to working with a relationship of coefficients in our polynomial that's negative 1 to the k power, and k is going to be that number, that number of roots that you're multiplying for each of these terms, times a sub n minus k. So a sub, now we're talking about the degree of the polynomial and the number of terms, the number of factors, that are in each of these terms, over a sub n, where k is greater than or equal to 1 and less than or equal to n. So we have a general form here of Francois Viette's formula relating the sum and product of roots to a polynomial. You have a specific list for quadratic, for cubic, and then an expanded list of this general formula we'd have down here in blue. Let's get to our examples right now. So for our first problem here that has got actually 5 parts, not are indicated 4, given the polynomial equation 2x cubed plus 6x squared minus 5x plus 2 is equal to 0, without solving this cubic function and finding those individual roots of x sub 1, x sub 2, and x sub 3, find or evaluate each of these expressions. And we're going to, though I gave you specific formulas for quadratic and cubic, which is what this is, a cubic polynomial, we're going to apply or look at this general form of Francois Viette's formula relating the product and sum of our roots to the coefficients of our polynomial. So when we look at our first expression here that we're trying to evaluate, it's just simply the sum of the roots, or each of our terms only has one factor, which means that k is going to be equal to 1. So this is going to be equal to negative 1 to the k power, the number of terms of, number of factors in each of these terms, so negative 1 to the first, times a sub, well, this is 3, or the degree of our polynomial, minus k, which is 1, over a sub 3. So we're looking at the opposite of a sub 2 over a sub 3. Or like our note said, it was the opposite of b over a. A sub 2, this is a sub 3, this is a sub 2, a sub 1, a sub 0. So we're looking at the opposite of 6 over 2, or negative 3. So we're able to find the sum of our roots without even knowing what the roots are for this cubic polynomial. Now here we only have one term that has 3 factors. So here we're looking at that fact that we're going to add over. That's kind of weird because we only have one term, but we're doing negative 1 to the k. Okay, negative 1 to the k, or the number of factors in our term. So it's going to be negative 1 to the third power times a sub 3, again that degree of our polynomial, minus k, which is 3, over a sub 3. Or in other words, it's the opposite of a sub 0, which is how we call it our constant in general terms, or you saw it as c with our quadratic and d with our cubic function, over a sub 3. So we're looking at the opposite of 2 over 2, which is equal to negative 1. Okay, fantastic. Now we are going to be taking the sum, again like part A, of some individual terms, but now instead of our individual terms only having one factor, our individual terms are going to be the product of two roots, or two factors, have two factors. So that means that we're looking at that this combination product sum is equal to negative 1 to the k power, the number of factors in each of these terms, so negative 1 squared, times a sub 3 minus 2 over a sub 3. Again, the n is the degree of the polynomial, k is the number of factors, the number of roots in each of these terms. So we're going to be looking at a positive, because negative 1 squared is positive 1. Well, of course we might have a negative coefficient, but we have a positive a sub 1 over a sub 3. So we're looking at, now remember, a sub 3, a sub 2, a sub 1, a sub 0. So we're looking at negative 5 over 2. And then finally, for our last problem here, we don't really have that sum or product or combination of sum and products. We basically have these roots of x sub 1, x sub 2, x sub 3 showing up individually in each of our denominators. So we need to algebraically manipulate this expression into a format where we just have a sum, a product, or combination of that, those two terms, or those two functions, with our terms. We need to find common denominators. So we have the fact that I'm just going to take, and we're pretty advanced now, right, if we're studying this topic, so I'm not going to show all these steps. We have three denominators of x sub 1, x sub 2, x sub 3, assuming that they have no common factors. We're going to multiply this first numerator and denominator by x sub 2 times x sub 3. Here in our second term, where we have a denominator of x sub 2, we're going to multiply by x sub 1 times x sub 3 to the numerator and denominator. And then finally, we're going to multiply by x sub 1 times x sub 2 to the numerator and denominator of our last term, giving us a single fraction with a common denominator of x sub 1 times x sub 2 times x sub 3. And our first term in our numerator is going to be x sub 2 times x sub 3. our second term in the numerator is going to be x sub 1 times x sub 3. And then finally we have x sub with our x sub 3 already in our denominator, multiplying again by x sub 1, x sub 2, we have x sub 1, x sub 2. And because we have already had these small sort of simpler examples in part A, B, and C, we have the parts that we already need. This numerator we just calculated to be negative 5 over 2, and the denominator, which is just the product of our roots, we just found in part B as being negative 1, so our final answer here is 5 over 2. And that's sort of the first 4 parts of our first example. Let me just double check. We got negative 3, negative 1, negative 5 halves, and positive 5 halves. Now let's look at our last part, part E of this example before moving on to our final last 2 examples. Now, for the last part of this example, we want to find x sub 1 squared plus x sub 2 squared plus x sub 3 squared. And like we talked about in our previous lesson where we were talking about the relationship of sum and product of roots for just a quadratic, and I erased the general form so I'd have enough room to write, because I don't want to just sort of spit out the answer. I want you to see all the algebra coming into this. I mean, look at all these parts so far. The sum and product of these roots with a power of 1, not a power of 2. So I can't just look at this and go, well, if x sub 1 plus x sub 2 plus x sub 3 is equal to negative 3, hey, each of these terms has a power of 2. Maybe this is just 9 because negative 3 squared is 9. No, it's not going to work, and let's hope it doesn't coincidentally come out to be 9. No, it's not 9. So we need to manipulate this expression into a format that just has the sum or product or combination of such, you know, restrictive in a format that you can do that, but we need all these degrees to be 1, not 2, and the only way you get degrees to come down is either through division or factoring. So, factoring. I need this to factor down basically to a point where it's something like the sum of 3 roots that have a degree of 1, maybe something squared, and some other stuff's going to be going on as well. So think of like x sub 1 plus x sub 2 plus x sub 3 squared. Can we get this into some kind of format? So at least part of it we would know that, well, actually be negative 3 squared, but there's going to be some other junk going on. Well, this trinomial squared is going to be obviously that trinomial multiplied by itself, and we're just going to have to distribute all of that out. So we have each of these terms in the first factor going to each of the terms in the second factor, and I'm just going to quietly write this out so I can speed up the video a little bit. Okay, so I just did that expansion. So we have x sub 1 squared plus x sub 1 times x sub 2 plus x sub 1 times x sub 3 plus x sub 2 times x sub 1 plus x sub 2 squared plus x sub 2 times x sub 3, as we've now multiplied our second term from the first group of 3 into each of the terms of our second trinomial. And then we're going into the x sub 3 times each of these terms, x sub 3 times x sub 1, x sub 3 times x sub 2, and x sub 3 squared. Okay, so we've got the fact that if we have x sub 1 squared plus x sub 2 squared plus x sub 3 squared, which is what we already have, and now plus 2 x sub 1 x sub 2s, because there's an x sub 1 x sub 2 here, and another one right here, plus 2 times x sub 1 x sub 3, because we have that term here and here, and then finally plus 2 x sub 1, whoops, nope, x sub 2, x sub 3. If I have these 6 terms factor back to be x sub 1 plus x sub 2 plus x sub 3 squared. And that sum of roots we know is negative 3. So I need to, with this expression, bring in the additional terms of 2 times x sub 1 plus 2 times x sub 1, well, I misread that, 2 times x sub 1 x sub 2 plus 2 times x sub 1 x sub 3 plus 2 times x sub 2 x sub 3. I just need to add those in. But I can't just change the value of this expression to suit my needs. Whatever operation I do to it needs to just simply change the way it looks. So if I'm going to add in these three terms, I need to subtract out those three terms. And maybe we'll do that in a different color. Great. Now, is that so great? Well, yes. Everything in yellow is going to factor back or become in factored form, parentheses, x sub 1 plus x sub 2 plus x sub 3 squared. Now, our last two terms, all of these have a common factor of negative 2. So if I take out that common factor of negative 2 and leave it as x sub 1, x sub 2 plus x sub 2, 1, x sub 3 plus x sub 2 times x sub 3. Yes, I actually find this to be fun. Hey, look at here. We've actually got an expression now that's asking for values that we already know. It's like I knew that was going to happen while I gave us parts A, B, C, and D. So the sum of our roots is going to be negative 3 minus 2. This combination of sum and products here came out to be previously an answer of negative 5 over 2. And so our final answer is going to be 9 plus 5, which is equal to 14. So that is really cool. I have a higher order polynomial that may be a bit of a challenge or take a little bit of time to solve, and was able to figure out all of the values of these expressions without ever actually solving that higher order polynomial. Got a couple more examples coming up right now. So we have find the sum and product of the zeros of these polynomials. Just the sum, just the product. So we're going to add just single roots or zeros of our polynomial. So we're looking at, for our general rule of Vieta's formula, k is going to be equal to 1. And the product, so just the straight product. So we're kind of like not really adding anything. We're just looking at the straight product of our roots. And we have a polynomial here which is to the 8th, has a degree of 8. So I don't really want to write as a sum, that it's x sub 8 plus x sub 7 plus x sub 6 plus x sub 5 and so on down until we get to an x sub 0. I just want to write the sum is equal to, well, negative 1 raised to the k power, the number of roots that are in each term. We're just talking about a straight sum, so that's going to be equal to 1, over a sub n, again our degree, minus k, so we're looking at a sub 8 minus 1 over a sub 8. So we want the opposite of the ratio of a sub 7 over, whoops, that's a big 8, over a sub 8. Well, here's our terms of our polynomial. We have a term that has a degree of 8, and we do not have a term which has a power of 7 or 6, or actually there's a lot of terms really missing if you want our powers to start at the highest degree and then count down by 1. Think about when you did long division and synthetic division. To make sure that those columns line up correctly, you have to fill in all those degrees or powers, and counting down by 1 until you get to a power of 0. Not degrees, because that's the greatest power. There is no a sub n, 7, which means its coefficient must be 0. So we're looking at the opposite of 0 over a sub 8, which is 7. Yeah, so our final answer here is going to be equal to 0. The sum of our roots that we have for this polynomial is going to be 0. Now what about the product? Well, that's going to be negative 1 raised to the k power, the number of roots that are in each term. Well, if I want to extend the number of roots that are in each term, I don't really want to add a bunch of individual terms. I just want nothing but roots. So k, it's going to be a product of 8 roots. So k is going to be equal to 8. And then we have here times a sub 8 as n, the degree of our polynomial, here the highest exponent, minus 8, because we want to multiply all 8 roots together, over a sub 8. So we have positive 1 over a sub 0 over a sub 8. Kind of like our what was it, positive c over a for quadratic, and the opposite of d over a if we had those specific coefficient labels for our cubic function. So a sub 0, our constant, is equal to pi, and a sub 8 is equal to 7. So the product of all of our roots is for this polynomial is going to be pi over 7. Double check. Yes. Now over here, where we have a polynomial to the 501st degree, and a lot of terms missing, we want to do the same thing. By now, hopefully, seeing the general form of Vieta's formula here, you can probably do this by yourself, but just to make sure, the sum of all of our roots, all 501 roots, is going to be equal to -1 raised to the 1 power, because we're just adding the individual roots, times a sub 501 minus k, which is 1, over a sub 501. So much nicer looking at this general formula and having one thing to memorize instead of your individual formulas for sum and product for quadratics and cubics and maybe 4th degree or something like that. It just gets to be a little bit crazy. So we're looking at the opposite of -5 over 4. I mean, come on, we just basically added 501 roots to a polynomial which we don't even know what those individual roots are, but yet we know the sum is going to come out to be 5/4. That's really cool. And the product of our roots is going to be -1. We don't want a bunch of individual sums or terms that we're adding. We want all 501 roots together. So k is going to be 501, and all that we really care about there is that we're going to have a -1 raised to an odd power, so it's negative, over, or times, excuse me, a sub 501 minus 501, n minus k, over a sub 501. Basically, again, with just the product, it's the constant divided the, well, -1 to the k power times the constant over the leading coefficient. So we're looking at -14 over our leading coefficient of 4. So we're looking at -7/2 for the product of all of the roots of this polynomial without even knowing what those individual solutions are. I'm Mr. True. Bam! Go do your homework.